Alrighty, good morning everybody. Welcome back to non-Euclidean geometry. Plan for today is I have a quiz for you on quadrilaterals as promised. And then after that we're going to continue our discussion of the history of, what was the third P? The Euclidean the parallel postulate. What was the third P? Proof, that was it. Parallel postulate proof history. That's right. I've got my usual office hours today after class and at 2, tomorrow at 10 and at 1. And here's your homework. This is a stressful time of the semester. Everybody's got papers and a bunch of things due. Didn't feel like assigning. I really didn't feel like assigning a homework today to be due like on Monday, this coming Monday, or even worse, the Monday after Thanksgiving. So go for a walk. Enjoy yourself. Relax a little bit. You probably need it.
Will the walk be on the test?
Yes. Yes, on the test.
The test is actually a race, but you can't run. Just a walk.
The test is a race where whoever comes in last gets the highest grade. No. On the exam, I'll totally be asking you questions about, suppose you were to take a random walk in a Hilbert plane. What can we say about the properties of where this random walk is likely to take us?
I don't even remember what the random walk is.
Oh, what's that there?
I said, is that differential geometry?
Surprisingly, yes. Well, random walks show up in a lot of different places in math, like discrete, differential geometry. It's surprising how much the idea of a random walk is. But no, this is for your own physical well-being. Take a half-hour walk on me. That's an order.
Walk on you. I don't know.
Don't walk on me or I'll race on you. Any questions or comments before we start today's quiz? What do you call a number that can't sit still? You call it a Roman numeral. Alrighty, go ahead and put everything away. It is quiz time. Go ahead and take a few seconds to finish up your thoughts. Okay. And pass your quizzes in, please. Trying to land exactly 1 second.
We do that at softball, we have stopwatches in the dugout for the runners. And they spend all day just trying to land it on 1 second.
Oh, it makes me feel good when I did it.
You get
Did I? How about there's some? Yeah.
There's got one more.
I got it.
Oh. Yes.
I just want to walk.
Oh, yeah. Go for a walk. Y'all actually want to go on a lap around the building?
Yeah.
All right. Optional exercise. Some of us are going to go take a lap around the outside of the building. If you want to, you can just, you're welcome to just stay here, but otherwise, here we go.
Maybe this will be the first probably one of the answers. You know what?
It's like a race days in high school where you're just like,
Yeah, let's go, bro. We're gonna get lost. We're gonna get left behind.
this is like a good. So, in case you all couldn't tell, I've tried to make this kind of a more chill class where we don't actually have like any major results we have to get to. So, we have time for side excursions like this. Anyways, back to math. So, if you recall last time we looked at Proclus's attempted proof of the parallel postulate, saw how it had a couple of sneaky flaws to it, or at least a couple of unjustified statements in there, including that it assumed Aristotle's axiom without explicitly saying so, or having that in a Euclidean plane. And then towards the end of class, we were starting to talk about this idea of having an equidistant locus to a line through a point. Or the idea is that if we have this line here, L, and the segment, PQ, that's perpendicular to the line L at a point Q, then the equidistant locus to our line, L, through the point P, is going to be the set of all points P prime that are on the same side of L as the point P, such that if Q prime is the foot of the perpendicular drawn from P prime to L, then PQ and P prime give us congruent segments. So in other words, it's the set of all points. Here would be another one, that if we took those points and dropped a perpendicular down to L, we would get a segment that is congruent to our original one, PQ. So P prime here would be a point in Euclid. So in like R2, for instance, here would be another one. Let's put P and give it a smiley face. Would be another point. And what do you notice about all these points in R2 for P, P prime, P double prime, P smiley face? What can we say about their relationship to each other, Jack?
They're collinear.
Yeah, they're collinear. Turns out, not only are they all collinear, but in fact, this line that passes through them is going to exactly be the equidistant locus 2L through P. That this equidistant locus happens to be exactly this line, I don't know, call it M here. So in R2, it's going to turn out to be the case that the equidistant locus to a line through a point is always going to be this line M that's going to turn out to be parallel to L. Parallel because it doesn't make sense to have a point on the equidistant locus that's also on L unless your P and Q are the same point, in which case they're not a line segment to begin with, and that's just weird. So here's my activity for you all. I've sketched a couple of line segments and lines, in one in spherical geometry, one in the Poincaré disc. What I would like for you all to do with your partners is to see if you can sketch what are the equidistant locus to L through the point P going to look like in these two scenarios, in these two other models of geometry, and see if you can notice anything, any interesting properties of the equidistant loci in these two scenarios that does not hold in the case of the R2 example we have right here. So go ahead and see if you can, working together, draw out what the equidistant loci are going to look like in these two examples, and see what's different about the equidistant locus here and here from here. And take a couple minutes, and as always, you're welcome / encouraged to work with your neighbors and see what you can find.
So then it must know what's missing. It's just the latitude limits.
And why did you sign up for a geometry course? Just because it's non-Euclidean doesn't mean you don't draw circles. Because it's your schedule. If you're forced to.
Oh, you're saying it's what's going on.
Yeah, like,
Yeah, with me.
Okay, so I think.
Like, it would go like this. Wait, what are you thinking?
Right, for sure.
Measure distance.
It's not a field line.
You will measure distance or
I'm just wondering about the other one. I don't know if it's gonna be a line because, you know, you need the right angle. You need the right angles on the edges.
Yeah, that's a good point.
So I'm not sure if you can get both.
Yeah, that's where my drawing skills.
Right, so you got this.
It looks like it could, like this is a chair. No, it wouldn't, because it's not
It's like a curve too.
No, not like, it would be like, have, at the top of that curve right there, you had a P that goes up, so it would be curving in this way, and then the way.
Oh, they would get longer. As
Yeah,
you.
I don't think that would work.
Yes.
Because this has gotta be a right angle there, right?
Right, and this
Oh,
is
and.
completely.
Let's see it.
Yeah.
So,
So then that would be like.
that's not a lot of this.
Sheesh.
Wait, no,
Wait,
but
let's
these
draw
are
it.
projections that way you
I'll be honest, I struggled with drawing.
Yeah, this one, the drawing is very.
What?
Okay, so these can just first.
Oh, yeah, the second
Yeah.
period.
Right, because it's just like.
Yes.
It's not like this.
Then
But
why do you
they
think
all
they
curve in the
should
same
do that?
direction.
But they've gotta be curving me more and more, don't they?
Right. So imagine
The lines themselves, like, you're just having them.
Wait a minute.
I think
This is like. No, I just,
Given the line.
I think it's impossible to write it somewhere. Think about where the edge of the pointer rate is. You're drawing your perpendicular.
There's definitely some tricky things to draw, I think.
So it's actually.
So,
They all be actual
in
segments.
the, well, either way, but even just the curve of this line, you have to be going in the same direction.
Doesn't have to be the exact same, you know, for it to be.
I mean, well, if you think about it, you just think about like rotate, like if you have something like, I don't know, like that. Like you could have these be congruent just because like if you were to rotate the sphere, suddenly this curve would start to look like that one. So yeah. And rotating the sphere is something that I would argue doesn't change any of the points of the line, it just changes our perspective on it.
And if you wanted to be the same.
Yeah, you could certainly have something like that be congruent to something like that.
But in the point group,
So
if you have a segment, if it's not part of a
And
line.
then
I think.
it's.
Segment always has to be part of a line. So like in this case,
Because if you move that one, it's the same curvature. If you move it over, it's not gonna be the right angle.
Probably wouldn't be so.
true. Yeah, but you could still have something like that congruent to something like that.
You'd find.
So there doesn't have to be a line.
I think you're only gonna get a segment.
Like maybe scale and multiples of another.
Because I'm, if I'm.
Oh, no,
Because look, I got this.
Like
circle.
why?
Because anything else
Or
won't work.
And I literally just shifted it just a little bit, and then it's thrown off my angles to the side.
So
How
you'd
unfortunate.
have to.
But I can flip it, I can reflect it over the
Which is
diameter.
allowed, I think that's allowed.
That is so funky, and I
But
hate that.
Or.
I think that those lines, if they're not, got it.
Yeah.
You make a line.
So, okay.
Yeah, so like, one line, that's-
You like an arc here, that is the same length as here, but I call it an arc,
Well, I have a
which
question.
means it's not.
It has to, no, by definition, like,
No, I mean like the line from.
they're not on anytime.
Like, yeah, these are all lines.
Which one are you looking at?
Yeah.
And then it moves
Yes.
to the line.
So we have the same L,
Oh,
But
yeah.
like,
You can't.
yeah.
like that, like that? What about
Can
it?
you count just like a part of it, like?
Instead of all points.
Yeah, 'cause
The
it's
side is just P and P prime. It looks like a
Or does
ladybug.
it have to include both of them? Because that's the only way I can find it.
No, this is not.
I don't know what you mean by can that only count part of
Can
it.
you like take a section
Just like
of
this.
the like
I mean, you could certainly talk about like having a line segment like that. Like that's a line, that is a, this right here is a line segment in the pointer array
I can shift it.
Which means that since the line is coming in right here, and it's not.
Absolutely not.
All I'm saying is this.
Like down here, yeah, you have to do it.
Not fun and crusty geometry. Geometry went from a block to real crusty, super.
Sorry.
I hope they can hear me on the recording.
Based on my drawings. Either it has to.
No,
He says, I'm sorry.
I'm still thinking about less, it's a great.
that's rather rude. Rudy.
Me and Arnold.
Yeah, okay.
Good one.
That's a great example.
It's too great.
So sad.
Maybe here.
Let's go ahead and take about 1 more minute and then we'll come back together.
What do you? I'm so, what are you talking to?
Okay.
How are you buckling?
So if we want.
You're not a wild bull.
Yeah. That goes to P, it's gonna end up producing F's for line.
I'm so tired.
I'm so tired.
I'm tired.
So we either get line M that doesn't exist.
My 11th line is over. I just have an essay
Or
and a
if we
presentation.
want, if we
I took a
want,
final yesterday.
this has to be a line.
But it's an oral.
Alrighty, let's come back together. Would anybody like to draw out what they found for the equidistant locus on the sphere? Ready? I'm going to show us.
So if this is P prime, another point on this, that's equidistant. So this is congruent with this. Then we have this, that is a terrible circle. Okay, it's not a great circle though. So therefore it's not a line and they don't create a parallel line because it has to be a great circle.
When you say it's not a great circle, you mean it's not well drawn or it doesn't enclose the maximum possible area?
Both. But for the point of this problem, it doesn't enclose the maximum possible area.
Gotcha. So we would get another circle on the sphere for our equidistant locus, but not something that's a great circle and therefore not a line in the model. Any questions for Megan? I like it. Nice job. And how about for the Poincaré? Wayne? Use the yellow. I just think it'd be easier for everyone to kind of see what you're calling the equidistant locus.
Okay, so for this one, what we had was just P and P prime are going to be in the equidistant locus, and that's because P prime, so this segment is this segment reflected over this diameter across the middle, but if you try to find any other points, you would have to keep the same curvature, so you'd be shifting this circle over a little bit, and that's going to ruin these right angles, so it's not going to even qualify as a line segment. Question?
Oh, I was just wondering if you could measure distance along the curved lines and then just go higher up as you get closer to the center. And then lower down as it bends more, but you can still travel along the segment.
You come up and maybe point out what you mean there in the back.
Oh, sure.
Thank you. And
Yes, thank you. So here it's a little curved, but if you like straighten it out, then this point will be a little higher. And that's also one.
We asked them, you have to keep the same curvature for it to be congruent.
Oh, it depends on if distances.
yeah, we never.
What's our metric?
I was the
I
same.
was gonna say. Yeah, well, we never actually defined really what it means for line segments in spherical or the Poincaré disk to be congruent. I'm going to define it now. Two line segments are congruent if you were to straighten them out; they would have the same length.
Yeah. Metric. All right.
Yeah, metric.
Yeah, and
Take
then
real houses from learn about it.
the weird part is as it curves, eventually you're gonna hit one that doesn't reach it. So it's going to start higher here and then kind of like decay faster, and then at some point there won't be any more equidistant loci. And I'm not sure exactly when that would be. But that's just because these are simply too short to get this length at the end here.
Basically, at some point, you're just going to bump into the edge of the circle, or the disc.
Oh, yeah, you're right. You would just bump into the edge of the disc at some point. Yeah. Yeah, like that. So it's kind of like a tiara.
Think of it that way.
Yeah.
Any questions for Jared?
Yes?
I guess, are you sure it's a tiara or is it more of a croissant?
Was that your question too?
Unfortunately, no.
Oh, okay.
My question was, how do you know that the tiara isn't a line on the Poincaré disc?
Well, this is a straight line. Wait, I'm not sure. Okay. It's because these won't be 90 degrees, and also this isn't a circle. It's more of an ellipse thing. It probably has two foci, but it might not. It might have no foci and be a parabola. But Dr. Gerstel will tell you that.
Oh yeah, I'll tell you that.
Yeah, but the point is the loci, the set that is the loci will not be a circle. So there's no way that it's a line. Oh, wait, what was your question?
How do you know that the locus doesn't count as a line on the Poincaré disc?
Oh,
How do you know
yes,
it's not gonna
because
be
this is not a circle. Why is it not a circle? Is that what you want to know?
Yes.
Does anybody have any ideas? Yes.
I was gonna say, I think it could be a circle, because you could also draw an ellipse for any of the other things that we've drawn. We're just assuming that it's a circle.
I guess circles are ellipses, it's true.
I would say it probably has to do with the angle at which it's hitting the edges.
Oh, yeah, you get the
So
angle.
because I think it would have to be an acute angle.
Yeah, an acute angle.
I think that's probably the easier way to see it, is just that the equidistant locus in the Poincaré disc is going to end up intersecting the outer disc at something that's not a right angle, so that circular or not, it can't possibly be considered to be
Yeah.
a line in the Poincaré disc. Thank you.
Because
Lost my train
in
of thought.
the Poincaré metric, it stays equidistant, but in the R2 metric, it's actually getting closer, see? And that means it's not a circle for some reason.
Yeah, this one is a lot more complicated. Thank you, Jared.
Yes.
What's it look like there? Yeah, the equidistant locus in the Poincaré disc is pretty gnarly and weird. But the moral of the story is, and the point I wanted to make is that in both of these cases, our equidistant loci are not lines. They may be croissants or tiaras, but they are not lines. Unlike in the case of R2, where this equidistant locus is going to turn out to be a line, and that is happens to be parallel to our line, our original line L. And in fact, if you flip the page, we actually have a theorem that's going to tell us in a Hilbert plane about the relationship between equidistant locus and whether or not it kind of forms this nice line. Turns out we can come up with 3 different equivalent statements. And first of all, the following are equivalent in a Hilbert plane. First of all, the plane is semi-Euclidean. Second is that I don't want to write this out, I'll draw a picture. For any line L and any point P not on L, so if this is our L and this is our point P, the equidistant locus is always going to be some line that happens to be that is a line through P perpendicular to PQ, where Q is kind of this, the foot of the perpendicular from P down to L. So in other words, condition 2 says that the equidistant locus for a segment, for a line L and a point P like this is you take the segment PQ that's perpendicular to L, you take the line that's perpendicular to PQ through P, and this M is going to be our equidistant locus. And finally, condition number 3 is Clavius's axiom, which basically just says that that given a line L and a point P not on L, the equidistant locus is just going to be a line that passes through P and is parallel to L. And it turns out that in a Hilbert plane, all 3 of these are equivalent. Let's see. Brianna, can you remind us what it means to have a set of like 3 statements like this and to say that they're equivalent in a Hilbert plane? What are we logically saying about the relationship between these 3 statements?
They're logically equivalent, so if you have one, you have all of them.
Exactly. Yeah. Either all 3 of these are going to be true in your Hilbert plane, or none of the 3 are going to be true.
Sorry, what exactly is Clavius's axiom?
Clavius's axiom basically just says that given any line L and a point P not on L, then the equidistant locus for P through L is always just going to be a line that is parallel to L. Not necessarily one that's perpendicular to the segment PQ inherently, but just some line that is parallel to L. And according to this theorem, these 2 conditions saying that equidistant loci correspond to lines turns out to be logically equivalent to saying your Hilbert plane is semi-Euclidean. By the way, what does it mean for a Hilbert plane to be semi-Euclidean? Kate?
You have 180-degree triangles, and your Secari and Lambert quadrilaterals are rectangles.
Yeah, exactly. We had kind of a few different equivalent definitions of semi-Euclidean. The original one is that triangle sums are 180 degrees, and that's equivalent, as we've seen in the last package, to having your Secari quadrilateral summit angles both be right angles, meaning Secari quadrilaterals are all rectangles, and also that the 4th missing angle in a Lambert quadrilateral is a right angle, meaning all Lambert quadrilaterals are also rectangles. So it turns out that that semi-Euclidean condition is what's necessary in order to have that your equidistant locus happens to be a line. If you have a Hilbert plane where that's not semi-Euclidean, where your triangle angle sums come up to something other than 180 degrees, what is happening outside here? Then your equidistant loci are not going to end up being lines within your model. Just like how in spherical and geometry in the Poincaré our crazy-looking equidistant loci turned out to be interesting-looking curves, but not things that fit the definition of lines within our models. Any questions or comments about that? I have some comments. All right, here's a question. What can we say about these 2 triangles? Elaine?
I already looked at the rest of the packet.
What a spoiled
Do you want me
sport.
to answer? Or?
What does it look like without using words from the packet?
It looks like they have the same angles, but not side lengths.
So that the angles all match up. There's a 1-to-1 correspondence between angles, even though the sides, there's Definitely not, because you said they're all way shorter?
Yeah.
Yeah. In other words, these are similar triangles. Turns out that if we skip forward now to the time of Wallace, several hundred years later, Wallace was able to find an axiom that maybe says something about whether or not in your Hilbert plane, whether the Euclidean parallel property is going to hold or not. And for that, we will see on Friday. So on Friday, we're going to talk about the relationship between similar triangles like this and the Euclidean parallel postulate. Quit looking ahead and spoiling yourself there, buddy. Well, ruining the fun. When we come back on Friday, we're going to try and see if we can finish the rest of this packet and then be ready to move on to part 2 on Monday. The PPP history. Have a good day.